at this example. I told you I give you a few minutes to try. I hope you try it and actually went through, experienced a bit of difficulty about choosing data. These data are still not the hardest to choose from. Okay, I ended off showing you this video, which I forgot to label for you the anode and the cathode. So here I actually labeled the anode and cathode for you. It's labeled by the color of the wires. Okay, so this is how we ended. You can see bottom right, you can see some yellow fluid forming. Left side, you will see some cloudiness, right? So when I ask you to fill up the page, did your predictions based on E0 values predict this? Did you predict the gas being formed? Can you see the slight pink that's forming? What is that pink? Did we all manage to account for that? Okay. So remember, for this topic, linking between E0 and your observations is actually a very important thing. See, the whole thing becoming very, very pink now. This is accumulation of this yellow color liquid. People at the back block. Shut up. Don't think because you're at the back, I don't see you. Do you want to come to the front to prove to yourself what I can see here? People in front, thank you. You're very cooperative today. People at the back. One more time, I don't care what class you're from, you will get it from me. Back block, do you understand me? Interestingly, I'm not even talking about this back block. Do you understand me? Do you? 6F, or 6E, I don't care, 3N, whatever. Do you understand me? Don't answer me. Whole block, stay back after lecture. Whole block, stay back after lecture. Idiots. Okay, please check. Cathode. At the cathode, the cations will go to the cathode. I also said at the cathode, reduction happens. So what you're looking for is species, the cation on the left side of the equation. Now on top of just the cathode being reduced, water also gets reduced at the same time. Okay, water also gets what I mean is there are two possibilities. One of them is the cation, the other one is water. How are you going to choose? Because reduction will happen at the cathode, and therefore you are looking for the more positive E0 value, which in this case is the one that corresponds to water. Okay, so water will undergo reduction. Just to remind you of a few things I said last lecture. Because you are quoting E0 values, you will use a reversible arrow. Okay? But if you are, because you have already decided what's going to happen here, you already decided that because this is the more positive E0 value, you know what's going to happen, please change it to the full arrow. At the anode, oxidation happens. You also know that anions tend to go to the anode, and therefore you are going to look for, because oxidation, right, all data given to you are written in reduction form. You are going to look for species on the right side, because only species on the right side can undergo oxidation. So I'm looking for a less positive E0 value, which is the one that corresponds to iodine, iodide. Okay? Your overall equation is as such. Okay, balanced by conserving the electrons. So one of the observations I want you to have, hope by looking at the video, is you realize hydrogen gas is produced. This is the gas that gives a pop sound with a lighted splint. Phenolphthalein turns pink because of the hydroxide. So be very careful about these kind of things. Some of you are very clear about gases coming out. You know, you forget about things that you cannot see, things like pH. Okay? And the anode, this yellow or brown solution that you see, why I gave you a range of colors because of concentration. Okay? Because of iodine formed. So observation electrolyte, remarks, key in yourself. Anyone still needs time? Four of you, last warning. Next time I see it, you're coming here. Don't try me. Don't try me. I'm very capable of it now. Look at me. Don't try me, yeah? Okay, move on. Okay, so what I've done here, you can actually do this at home. It's supposed to be a fun lecture, but with you all like that. Okay, so you're supposed to be able to do this at home. What I did is I took a plastic cup. You know when you buy IKEA furniture, they always give you a lot of spare nails. Okay, so I actually kept those spare nails, drilled into the bottom of the cup. Okay, so it looks like that. And what I did was I connected it to a 9-volt battery. You can actually do this at home. It's actually quite easy. It's quite fun. You actually see a lot of things that you don't expect. Okay, so let me give you the situation here. You try and solve the problem for me. Okay, predict what I'm going to see. Here is the negative electrode. This is the positive electrode. Those are iron electrodes. Okay, those are iron nails actually. Okay, and you can treat this effectively as water. So try for me now. Predict what do you think will happen. What do you think I'll see? Okay, can maybe give you 2 minutes. Try. Not too difficult. Okay, try now. Take out a data booklet. Look through the data. You can discuss if you want. You can chit-chat if you want. When I need you to be quiet, you be quiet. Okay, but if you need to discuss, you want to talk, fine. Okay, 2 minutes. Try it now, please. Did we predict something? Yes? Okay. Hey. Okay. Sorry, people. This happened this morning. Sorry, so you won't see the correct things already because the color is off already. It happened this morning, but it happened. The color change happened after I showed the video. Anyone predicted gases on both electrodes? Gases on both electrodes? Okay, good. Okay, so let's try this. Anyway, what I wanted to... Okay, so what I did is this. I didn't want to let everything escape. I actually collected in a test tube. Anyway, at the back is my kitchen. That's my KitchenAid if you're interested. Okay, so I collected it over test tubes. I do have test tubes at home. So what happened is this. I will let it run. I want you to see whether it is consistent with what you know. Okay, so that is a 9-volt battery. That is a 9-volt battery you can buy. It's $350. Nice, right? That's why you use 9-volt. Okay, we use 9-volt because a lot of current, a lot of reaction. Okay, why 9-volt, a lot of reaction? Let's look at the last part, Faraday's law. Can you see all this? Let's just admire the beauty of it for a while. It's actually quite beautiful. I wonder what I did with the hydrogen gas, but never mind. Okay, can you see a lot of hydrogen gas accumulate? Oops. Can you see a lot of gas accumulating here? The other side have or not? Nothing, right? Do you predict something will happen here? You did, right? But sorry, not my fault. The screen is not cooperating. I'm going to fast forward it. Okay, what I'm going to do at the end is now I'm going to remove both tubes. I'm going to just plug out both tubes. You know what will happen? Can predict? Sorry, but you can't see it. Let's see whether you can see it. Am I going to do it? Yes, I am. Oh, you can. You can see it. Do you see it? The color is correct, I think. What's this? Sorry. Hey, the color is correct now. Oh, you saw it? What is that? Okay, what is it exactly? Let's run through this, okay? Because without some text on the screen, very hard to discuss with you. Okay, so I use this data. Negative electrode, I'm sure you know, reduction. From all the effervescence you were seeing, I'm very sure you know it is the reduction of water to give you hydrogen gas. So, but remember earlier example I was trying to tell you, don't focus on just what you can see. There are a lot of other species there that has effects that you cannot see. For example, the hydroxide, right? Okay, at the anode, oxidation happens. Oxidation of what can happen? Okay, the anions, right? Okay, but no anions here, sorry. So what can happen is iron, electrode can undergo oxidation, or water. So at oxidation, I'm looking for the less positive one, which is in this case, iron. So iron will become iron 2. Now, if you have done your QA well, you will realize this. Iron 2 green. Okay, iron 2 solutions are green, right? But it's very, very hard to see. I hope you realize that when you point inside a test tube, you cannot really see it. So what happened when I remove the test tube? When I remove the test tubes, what did I allow to happen? I allowed them to mix. Okay? So my hydroxide from one end mixed with the iron 2 from the other end. The flourish of green that you see is actually iron 2 hydroxide. It's actually a precipitate. Okay, how do I know it's a precipitate? Actually, I wasn't convinced it's precipitate, but I went to wash up after that because I created a mess in the kitchen. Okay, then I left it to stand. What happens when you leave iron 2 hydroxide to stand? Turn reddish brown. Okay, so my whole cup started turning reddish brown. Okay, so this kind of experiment is very easy to do at home. This table is an IKEA table. It's where I got the nails from. It's the extra nails from fixing this table. Okay, you can try it at home. It's actually quite easy. Ask your parents for permission first. Okay, some people at the back were actually asking me, is this pure water? To be honest, I cheated a little. I need to make water conduct electricity better. So I use salt, sodium chloride. Okay, I added a bit of salt, just a few pinches of it, just throw it in, I didn't even weigh it, just to make it conduct electricity better. Okay? Now this next section is about applications. Normally applications, we tend to tell you, can you please self-read? In this case, I'm not going to ask you to self-read because it tends to come out. Okay, it has come out a few times already, so I'm going to spend some time on it. But I'm very sure you're able to understand, so I'm going to go through a little bit more quickly. Okay, so what you'll see is aluminum has a E0 value of minus 1.66. If you actually study your data booklet like I have, you realize that this is one of the most negative values on your data booklet. There are values that are more negative, definitely, but this is one of the more negative values around. Okay? This tells you that actually the equilibrium of this, the position of this equilibrium lies quite far to the left, right? You know what the sign tells you, correct? Now, because it is so negative, you would think that aluminum is actually very reactive. You would think aluminum is very reactive in a sense that it wants to become the Al3+. But you find that it actually doesn't really like to react. What happens is, interestingly, there is a layer of protective aluminum oxide. This layer is formed from reaction with oxygen in the air, but it's very thin. It's very thin. So scientists, what we like to do is we decide that why not let's exploit it. Let's make it even more. I want to protect aluminum even more. Let's make an even thicker layer. Oops. Let's make an even thicker layer. We're going to do anodizing. Now, in anodizing, what we do is we put the aluminum object at the anode. At anode, oxidation happens, but it is oxidation of water. Oxidation of water happens to give you oxygen gas. The oxygen gas that comes out actually reacts with the aluminum to give you aluminum oxide. Okay? I want to show you this video of the usefulness, how important anodizing of aluminum is. Most of you have it in your pocket. I think a lot of you have it in your pockets now. Okay, so just...
I love the unibody design Apple uses in their laptops. They're made from aluminum, or titanium, that's processed to give a polished and refined look with a tough surface. They use a similar process on their iPods as well. The colorful aluminum cases look painted, but the surface is actually a layer of aluminum oxide growing into the aluminum with a dye locked into it. What's really bizarre is that these layers come from carefully controlled corrosion, in other words, rust. Every piece of aluminum develops an airtight oxide coating on its surface almost immediately when exposed to air. Now, while we think of corrosion as a force of destruction, when used creatively by engineers, it can yield incredible utility as seen in Apple's products. To create the coating used on these products, engineers enhance the growth of that oxide layer electrochemically. Let me show you with a piece of titanium. I've placed a strip of titanium in this solution hooked to a power supply. Don't do this at home. This can be lethal. Watch what happens as I apply voltage. We see bubbles coming off the electrodes. As I increase the voltage, the color of the titanium changes. We call this process anodizing. Here's what's happening. I'm growing a layer of titanium dioxide. There's a very thin layer there naturally, but as I increase its thickness, you can see the color changes as well. If we look at the strip I created from the side and exaggerate the scale, we can see that each color corresponds to an oxide layer of a different depth. The color comes from the interference of light rays that bounce off the titanium surface at the bottom of the transparent oxide and those that reflect from its surface. The thickness of the layer determines how those two rays interfere. For each thickness of the oxide layer, two waves of a specific color will be exactly a half wavelength.
Physics students, what's this? This is similar to Young's double-slit experiment, right? Optical path difference and everything. It can cause color to be observed. It's quite interesting, right? Never knew you could understand color from that, right?
Out of phase, and so when they recombine at the surface, they cancel each other. The color observed then, if the light source is white, will be the complement of that color. Well, titanium is fascinating. Anodizing is of most importance for aluminum because the coating can be made thicker, more robust, and protective. To get vivid colors, we dye the aluminum and seal the surface to lock in the color. Anodizing aluminum starts out much like titanium. Using aluminum as the positive electrode, engineers first pass enough current to grow a thin barrier layer, similar to that which forms naturally. Then, as the anodizing proceeds, the current pushes this barrier deeper down into the aluminum, converting the aluminum above into a very porous oxide layer. It isn't a layer being put on top, but instead the reaction consumes and converts the aluminum. This is one of the reasons it's so effective at preventing corrosion. The pores in this layer give the aluminum a unique characteristic important for a consumer device: the ability to be colored. The pores formed on the surface have a honeycomb pattern. Inside these layers, one can place dye of any color. Once the pores are filled, engineers seal the layer by boiling the aluminum in hot water. This closes the pores, locking the color in forever. You cannot scrape it off without removing the aluminum. The toughness comes from the oxide being structurally similar to tough gemstones. Sapphire is an aluminum oxide with trace amounts of iron and titanium to give it a blue color. It's also the basis of ruby, the same crystal structure with chromium that absorbs yellow-green. Both materials are very hard, 9 on the Mohs scale. In a typical iPod, they use only soft anodizing, so that layer isn't quite as hard, but still more durable than paint. I just love anodizing.
How many of you can say that with a straight face? I love anodizing. Okay? So you can see it's actually quite useful. I don't suggest you try and scratch it, but if you accidentally scratch it, you realize even if you scratch it, you can see color. No, it's not the case that when you scratch it, then you see a gray layer underneath. No matter how much you, okay, maybe not no matter lah. A small scratch, you actually can see pink, 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 pink. It's still pink all the way through. Quite interesting, right? Quite smart use. Okay. Now this one, less, not likely to be in your pockets. Okay, but yet a very important process. Now, this has come out twice already, which is why I want to spend a bit of time on it. So, in impure copper, these are the main impurities. I'm going to choose 2. I chose to focus on zinc and silver as the particular impurities to focus on because they have something for me to teach you about. So let me just quickly go through what happens to copper first, because the idea is I want to purify copper. Now, when you do electrolysis here, the impure copper is placed at the anode where oxidation will happen. The idea is this: when oxidation happens, copper is oxidized to copper 2, it enters the solution. Okay, it enters the solution where it can possibly travel to the cathode where it becomes reduced and be plated on the current copper metal. Okay? What you will see is, as a result, as time goes by, the anode will start dissolving because most of the copper is going over, and the cathode will start getting bigger. Will start to get bigger. Sorry. Okay. Yeah. Now, what happens if you have impurities with E0 that's more positive than copper, such as silver? Okay. Very hard to imagine, right? What does more positive mean? Let's take a look at this. Because we are at the anode oxidation happens. So you're going to focus on species that can be oxidized. This will be the species on the right side of the equation. Okay, so you realize that because the E0 for the copper half equation is less positive, the copper, it is more likely to undergo oxidation, which is why copper is preferentially discharged. And what will happen to silver? Silver cannot be oxidized easily, and therefore it will drop to the bottom. It will fall to the bottom as sludge. You might want to take that down, please. Okay, this question has come out in 2 forms. Both forms require you to state everything from scratch. Okay? Including providing your own examples of impurities, meaning you need to be aware that possible impurities include zinc and silver. Zinc falls and drops. So the silver impurities will not be oxidized, they fall to the bottom as sludge. You can just filter them, collect it. Okay? Done? Now, what happens if my impurity has an E0 less positive than copper, such as zinc? I put them side by side because I didn't have enough space. Now, what happens is this. At the anode, again, oxidation happens. So you realize that zinc's E0 is so not positive. In fact, it's so not positive that it's negative. Zinc is most likely to undergo oxidation first, which is what happens. Zinc will undergo oxidation first. When all my zinc has been oxidized, then my copper will start to get oxidized. Okay? But next thing will be, will my zinc end up on my copper cathode? If so, my poor copper cathode will be contaminated with zinc, right? Again, let's look at the E0 values, because at the cathode, reduction happens. So let's see, is it possible to reduce zinc 2 plus to zinc easily, or copper 2 plus to copper easily? Looking at the E0 values, because now you are looking at cathode, the zinc E0 value is too negative. Compared to copper, it is not going to be easily reduced. So copper is the one that's reduced. And what happens to zinc then? Zinc remains in solution. Okay, your zinc actually remains in the electrolyte and is not plated. Meaning, diagrammatically, you realize that the oxidation of zinc 2 plus to zinc metal is not going to happen. Through this process, I managed to separate both. One of them, silver, by letting it just drop to the bottom, because it cannot be oxidized. Zinc can be oxidized easily some more, but it cannot be reduced easily. So I separated them, right? Okay, moving on. Okay, electroplating is very similar concepts to the first two. Please read it yourself, thanks. Okay, I'm going to end off with the last-ish part. Faraday's law. Physics people, you may know it very well, but please give me some time to explain it. Faraday's law, to put it very simply, talks about how the mass of substance produced, or the volume of any gas produced, is dependent on the amount of charge that you pass through. Symbolically, it says that M, which is the mass in grams, is proportional to Q. Okay, capital Q is the symbol we use for charge. It is the amount of charge in coulombs. Okay, so coulombs is a unit of measurement, C. How I can find the amount of charge that I'm passing through a circuit, it's actually determined by the battery. For example, how strong is the current that I'm passing? The current is in amperes, which is capital A, and it depends on the amount of time that I pass the current through. Now, the time must be in seconds. Okay, so please take note of that, your units. As with all equations, please know the proper units to use. For example, PV equals nRT, what are the proper units to use, okay? The amount of substance formed based on this equation shows that it's not dependent on temperature or concentration. It depends only on charge. So to give an example, let's say if I increase the amount of charge, with greater charge, it means that I'm passing more electrons. So if you see as a reaction, when I'm passing more electrons, I'm going to actually get a greater mass of product. Okay? And how do I get a greater quantity of charge? I can actually, look at this equation here, either use a stronger current, change the battery, use a stronger current, or I can use the same current but increase the amount of time that I use. Okay, or any combination. Okay, increasing concentration of CO2 plus has no effect on the mass of the product. Which leads me to Faraday's constant. Now, Faraday's constant is very important because it actually links charge to number of moles. Don't forget, when you do any chemistry calculations, you realize that, in terms of, you want to do chemistry calculations in terms of calculating mass, calculating volume, you realize you must link back to number of moles. And how do you link an electrical quantity back to number of moles? You need to use Faraday's constant. Okay, 1 Faraday is the charge carried by 1 mole of electrons, which makes this equation actually quite intuitive. E is the charge of 1 electron. Okay, I remove the negative sign now. E is the charge, the magnitude of the charge of 1 electron. L is actually Avogadro's constant. Avogadro's constant tells you the number of particles in 1 mole, right? So multiplying this together, it is literally the charge carried by 1 mole of substance, which is 96500 coulombs per mole. Don't worry about memorizing this number, though if you practice enough, it will be ingrained in you. The number is available in your data booklet, page 2 or page 3, can't remember, it's there. So is the charge of electron, I think it's 2 spaces below, okay? So let's use an example. If the total charge that's passed through is Q, then the amount of electrons is just number of moles of electrons. What am I talking about? The number of moles of electrons is just Q over 1 Faraday. Because remember, 1 Faraday is 96500 for 1 mole of electrons. Right? So if I have Q coulombs, I can find the number of electrons quite easily, and I can derive this second equation. Now, once I introduce this second equation to you, I need to clarify something with you, because it may cause you some problems in your mind when you do this tutorial with Electrochem 1. And next slide, I'm going to compare and contrast these two for you. Okay? This one, Q equals NEF versus Electrochem 1, delta G naught equals to negative NFE naught. A lot of people mix these two ends up. They don't mean the same thing. Okay, just to clarify, this for the left side, Q equals NEF, this NE, number of moles of electrons pass through the circuit. It's the number of moles of electrons that's passing through the circuit, so it is actually an actual number of moles. Okay, what do I mean? Let's say 1,000 coulombs of charge is passed through the circuit, right? Because I know that 96500 coulombs is for 1 mole, I can find 1,000 coulombs. 1,000 coulombs is just 1,000 divided by 96500, I can get 0.0104 moles. This is a physical, actual number of moles, okay? But the other one, Bisma has defined for you quite clearly, I hope you were paying attention. This is the number of moles of electrons transferred in the redox equation. This is not a physical number of moles, this is actually what you write in the equation. Let me give you an example. Don't have to copy this example, it's from Electrochem 1. I copy and pasted it. This overall equation came from these two half equations, right? In order for me to combine these two equations together, I needed to have multiplied the silver equation by 2 so that the silver equation has 2 electrons, right? Then I can combine the two. Effectively, what this told me is, in this reaction, 2 electrons are transferred. Okay, sorry, 2 moles of electrons are transferred. Okay, so here, amount of electrons transferred in the equation is 2. Okay, so please be careful. If you want, can you take a photo of this or write it down or whatever? I'm going to give you 10 seconds only. Okay, take a photo of this if you need. Make sure you never make this mistake. If you do your TYS, you will find that this equation is defined for them. They actually very nice, define everything for them. But that's because in the previous syllabus, this wasn't in the syllabus. This is in your syllabus. If you're asked to use it, they will not define it for you. You have to know what each term means, okay? Okay, so get it down. Make sure you don't confuse yourself. Okay, let's go to Faraday's second law quite quickly. Faraday's second law easily understood with an example. So look at this example here. 1 mole of sodium requires 1 Faraday of charge. And how you decide that 1 Faraday, look at the charge of the ion. Mg2 plus is 2 plus, therefore I need 2 Faradays. Aluminum 3 plus, it will be 3 Faradays, assuming I want to discharge 1 mole of each. Okay? So let's go through some examples with you so that you can understand how to use them. I will show you 2 methods. Up to you which one you want to use, because both are correct. I actually prefer method 2. Okay? But method 1 is conceptually sound. You make use of concepts to do it. First, we can calculate the quantity of charge. It is the current times the time. Now, please don't forget, the time that you use here must be in seconds, so I convert the 20 minutes to 1,200 seconds. I write down the equation, because I'm trying to form copper, so the copper must have come from oxidation of copper 2 plus. Because copper has a 2 plus charge, like what I just said earlier from Faraday's second law, I need 2 Faradays of charge. Okay? 2 Faradays of charge to form 1 mole of copper. But here I only have 2,400 coulombs of charge. Mathematically, to find the amount of copper is just 2,400 divided by 2 coulombs. You can get the amount of copper, you can find the mass of copper. Okay? Method 2 is the one that I hide some of the numbers from you. You might want to take it down. I like this method because it's very fast. I told you that Q is equals to IT. I also told you Q is NEF. Why not just merge the 2 equations together? Right? From here, I can find the number of moles of electrons very easily. Once I find the number of moles of electrons, let's look at the equation. Okay? So what you know is the number of moles of electrons that were used is 0.02487 moles. You can find the amount, the number of moles of copper formed. It is just half. Okay, so I'm doing simple stoichiometry now. I'm treating my electrons as a reactant. Okay, I'm treating my electrons as a reactant. So it's number of moles of copper formed is just half that of the electrons. I can find the mass. Just use the number of moles times the AR. Okay, answers exactly the same. Find this method a bit shorter? Don't know, up to you. Okay, if you're done copying, can you try example 3 on your own? Work example 3. I've given you example 2. Can you try example 3? I've inbuilt a few traps for you to try and fall into. See whether you fall into them. Okay, just try it. Give you 3 minutes, 120. It shouldn't take too long. Example 3 can come out as an MCQ, meaning 1.5 minutes. Okay? But here I give you 3, just try. Okay, take out your data booklet, discuss if you need to, try. I always say the same thing. You are here, don't waste your time. Okay? Do it now, force yourself to learn something. Go back, you have more time to do other things. Okay? You take out your data booklet, try it now. Those of you who are trying, you realize something, right? Some of you are stuck at the first stage. You're trying to find an equation to use. This topic is always like that. You're always trying to find the correct equation to use. Practice more helps, so do it. 1 more minute, I hope you find the equation quickly. Okay, don't have much time. Shall we try? Hope you found the correct equation. Okay, if you practice enough, you will know exactly what equations your teachers know, okay? When I see this equation, I will write, so anticlimactic. I'll write this straight away. Okay, oxidation of water. That is how I get my oxygen gas. How long did it take for you to find the equation? A good 2 minutes, right? Okay. Now, once you are aware that this is the equation you have to use because this is the one that produces oxygen, it's actually from the oxidation of water. I use my favorite formula, NEF equals to IT. Just a reminder again, convert your time to seconds. Okay, 9650, then divide by 96500. You will get the number of moles of electrons. Now, because the number of moles of electrons is not, you can see it in the same half equation, you can actually relate it to the number of moles of oxygen formed, which is just 1/4 that of the number of electrons that has passed through. Right? STP. What's the volume at STP? What's the volume at STP? 22.7. Why 4? Some of you mouthed 4. Huh? It's okay. Doesn't matter. You're trying. That's good. Thanks. Okay? It's 22.7. Okay? Because stoichiometry, more concept is being tested for your Common Test 2 and your prelims at your A-levels. Please know this kind of quantities, 22.7. And you have your data booklet in front of you. It's in the data booklet. Right? Okay, take this down quickly. Done? Your level of noise tells me you're done. Okay, last example. There are things for you to take down. Okay, it may look very small so you can't see. Actually, there's something to take down here. Okay, here there are things for you to take down. Okay? Shh. Now, these questions are quite common. They are complex because now I have 2 cells. But please remember, because they are connected in in series, what you know is that the same amount of electrons will pass through both setups. Okay, the same amount of electrons will pass through both setups if they are connected in series. So what I'm going to do is I'm going to write down the equation for what I know is going to happen. The question actually helps you. I started with X sulfate, it becomes X, right? So X2 plus must be reduced to X elemental, okay? Here is Y plus becoming Y. So actually I know the 2 equations that are happening. But you realize I did something strange. What I did is, by right it's just Y plus 1 electron gives you 1 Y. I multiplied by 2 throughout. Because in series, you will find that the same, I see it as an easy way to see it. Okay? The same number of moles of electrons will pass through both setups. And therefore, by equalizing, by making the number of electrons the same, I can actually see that the amount of X produced versus the amount of Y produced. You can see that there is more Y formed for the given amount of charge that passes through. So the amount of X is actually half the amount of Y. Okay? Now for this kind of problems, usually you are stuck here. You cannot get past here. Once you get here, the rest is very easy, which is why I printed everything for you. Most of you will get stuck here. You cannot form this relationship. The moment you form this relationship, the rest becomes very intuitive. Because you look at the question, they want me to find ratio of masses, they give me atomic mass, mass over AR is actually number of moles. So it's very intuitive that you actually break down number of moles to mass over AR, right? Then you do some mathematical manipulation. Using the data you are given, you can find the ratio. Okay? Actually, there's one last thing I'll discuss with you. I won't, but you might want to spend some time thinking about it. Beginning of this lecture, I started with this Daniell cell. I asked you to explain to me why, in principle, this process is called charging, but it will never happen in real life. A Daniell cell cannot be charged, meaning I will never get it to look like this again. Okay? Use some data, go and try it. You can look for me, we can discuss it outside of class. Okay? People, next week's lecture is on periodic table. Please collect the notes. Thank you.